Thank you to you guys for joining us for our first sustainability coffee chat of the fall 24 semester. We've been doing this for a few years now. I see some familiar faces, some new. My name is Carly Rice. I'm the sustainability coordinator here on campus, she, her pronouns. Um, and I'm thrilled to have two fantastic speakers with us today, speaking on their climate research relating to ice cores, which I think is fascinating and a topic that I certainly don't know enough about. Um, you'll notice that these sessions generally have a climate focus the past year. That is because we've recently um, released and are beginning implementation on a new climate action plan for the Twin Cities campus. So we are all about climate all the time. So we'll be getting some great information from Peter and Julia today. So with us, we have Dr. Peter Neff, who is a glaciologist and climate scientist here in the Department of Soil, Water, and Climate. And we also have Julia Andreasen, who is a PhD candidate in the Neff lab. So they're going to be speaking on their research, and then we will have plenty of time for some questions and informal discussion after they give their introductions. We like this to be very conversational. So please feel free once they are finished with their introduction piece to ask questions, and we will kind of just continue with a nice discussion here on our Friday morning. All right, so with that, I am going to stop my share and I will turn it over to Peter and Julia, and feel free to run this however you would like.
Awesome. Yeah, well, thanks so much for having us. I do have slides that I hope will be engaging for folks and foster conversation. And it's meant to be sort of like a little bit of Ice Core's 101, the sort of climate information that we can provide through the Ice Core record. And then also a bit of a travel log, because Julia and I have been quite busy over the last year to 12 months collecting I guess, three new ice core records in very different far-flung parts of the world. So I will share my screen. Of course, it's now okay, let's see. And I have a little bit of ice core data that I want to put in front of you, but not that much because I know it's the morning and it's a Friday. Um, so is that you can see my slides nice and there?
Yeah.
Cool. So yeah, I'll go over what we've been up to in the last little while, and we'll get the classic, like I can't see my mouse on here, but whatever. Let's see. Sorry, it's odd, odd mouse issues. There we go. Okay, look good again. Sorry about that. So we'll be talking mostly about this last most, I guess, wildest expedition that Julia and I went on last December, January, February, down to Antarctica, sort of the very southern end of the Pacific Ocean on a South Korean icebreaker to get out to this location, this big pancake of ice where we drilled some cores and got them back onto the ship and returned home. But first, I'll go over a few University of Minnesota connections to Antarctica. So we have a few faculty members over the years who have worked there, and some of the very earliest U.S. science in Antarctica was done led by the University of Minnesota. So there are some Minnesota names sprinkled across this part of Antarctica, named after either the individuals on the team. Robert Rutford was a Minnesota guy that did a lot of degrees at the university and was an early leader in U.S. Antarctic science. We got Minnesota Glacier, Gopher Glacier, Pillsbury Tower, named after Pillsbury Hall, which was originally the geology building. And we actually were quite near where a lot of these names are at Canisteo Peninsula, that little dot there on the right where Julia and I went most recently. Um, let's see. So we work with glacier ice, which begins as snow falling on the surface of a glacier. And when we are thinking of places to drill ice cores, we go to the places where snow never melts, or it melts as little as possible. so that we have each layer of snowfall going back in time, that we can either study the chemical composition of impurities that get attached to the snow, things like dust or soot or salt from the ocean, that we can use to reconstruct environmental conditions. And then the ultimate direct sampling that ice cores do for us are these air bubbles you can see when it zooms back and forth to this piece of ice that's from about 100 meters deep. We have air bubbles in glacier ice that are direct samples of the atmosphere in the past, so we can reconstruct greenhouse gas compositions, which from a climate perspective are really, really important drivers to keep track of for for how that affects the warming of the atmosphere. So my little overview, one sentence about what we do with ice cores is that we use ice cores to explore climate processes, trends, or extremes in locations and or at times where we wouldn't otherwise have observations. So Antarctica, have very few observations. We have very few climate records in mountain environments. And so those are some of the things that we've been working on. And getting those records, these time series going back hundreds to even millions of years, give us perspective on climate, environmental, glacier, and ice sheet sensitivity in a warming world. And I guess I always end on that in the warming world setting, because that's really my motivation to be in this research, is to use ice cores to give us context in all of the critical places of the world where we need to know what the climate's been doing in the past and how it's changing now, knowing that our influence, because we're emitting a lot of heat trapping greenhouse gases, how that's changing systems that are going to lead to things like sea level rise from melting glaciers in Antarctica. So again, the really cool direct samples in any glacier ice. This is ice from our site that we went to last summer 2023 in British Columbia. So whether it's British Columbia or Antarctica, there are still bubbles in any glacier ice because it started as snow. And as the layers stack up over time, the airspace between those fingers of snowflakes gets trapped into bubbles. And once you go deep enough, then you can drill these cores that have beautiful bubbles of air and then also the snow that we study. To look at this process in a diagram, I think this is one of two diagrams that I have, so don't worry, it's not going to be super intensive before we hop into our recent field work. But if you look at the surface of a glacier, it starts as low density snow, which has airspace between it, and it takes about a stack of 100 meters of snow to compress that airspace into a solid bubble that's then isolated from the atmosphere and is our sample of the past atmosphere. And so that's why we drill deep. So the cores that Julia and I have been working on in the last year or so have been 150 to 220 meters deep. And that's also just a depth that fundamentally is how deep we can go before drilling starts to get a lot more technical and need a lot more complicated equipment. And I wanted to step through really quickly, if I stop my slideshow here, step through our record of greenhouse gases, both from atmospheric observations and then connecting back to the ice core record. So if you go to the Keeling Curve website, this is an iconic data set that's ongoing, measuring the atmospheric concentration of CO2, so the most important long-lived heat trapping greenhouse gas in the atmosphere. So our concentration in the last week or so is up to 420 parts per million. And this website has nice little graphs that you can step through from the last week of data to the last 6 months of data. The last 2 years, you can see there's a seasonal cycle of CO2 in the atmosphere due to how trees uptake CO2 during the different seasons in different hemispheres. The full record of the Keeling Curve goes back to 1957, so continuous atmospheric observations over that time. But before then, we don't have any direct record of CO2 in the atmosphere except for from ice cores. So you can then connect the ice core record here if we go back to the year 1700. So connecting with the Keeling Curve, the ice cores, this is taking an ice core, breaking up those air bubbles that are in the ice and measuring the CO2 concentrations from that. They connect directly to the atmospheric record. And if you start going back then 2,000 years, you see just how drastically we've changed the atmosphere during the industrial period. Go back 10,000 years to see it's much the same. And if we then put the full ice core record on here, we go back with deep drilling in Antarctica, ice cores that are about 2 miles long. You have an 800,000 year record of CO2, which goes up and down during warm periods and ice ages every 100,000 years or so. And again, you can see just how rapidly and how far off the scale we've gone with the greenhouse gas emissions from industrial activity as humans. So that's sort of a lot for a Friday morning, I suppose, and we can talk more about that. But I really like being able to just click through this and show how the ice core record connects to our modern observations of greenhouse gas concentrations. And it also applies to other climate variables like temperature or wind strength and things like that. So Julia and my work contribute sort of to the bulk of this in different ways, and we can talk about that more. But what I want to do now is more of a travel log of our more recent work. So let's see, I'll start here with what we did last summer. So last summer we spent a month and a half in southern British Columbia, about a day's drive north of Seattle, not too far north of Vancouver, British Columbia, drilling an ice core to bedrock in a mountain setting, which is a place that I've been working on for about a decade, where we know that the snow is just cold enough to preserve a record there in this really far southern region in North America. That allows us to get a hopefully 200-year long record of climate in this mountain environment. So we were up at the site for I think 2 weeks, drilling this ice core to bedrock, and then getting it off and back to freezers where we can study it. And so this ice core now is at the U.S. National Ice Core Facility in Denver, Colorado, where we sample cores. We cut them up into samples to then do chemistry on the different layers through time. And this project really fed into the work in Antarctica last December, January, that sort of directly came from this project's, in our experience of this size and operation, and using helicopters to get to our field sites and get all of the thousands of pounds of gear we need up there to drill cores, and then get the cores back from the site and into a freezer. So doing this in the mountains sort of let us do one run through of this before needing to do it in a really extreme situation down in Antarctica, which is this, joining the South Korean icebreaker Aran for a journey across the southern Pacific Ocean to a really remote part of Antarctica to get some new ice cores from a really fast changing but poorly observed part of West Antarctica, which is the part of Antarctica we're most worried about changing relatively soon and continuing to contribute to global sea level rise from now and into the foreseeable future. And so we were under really crazy time constraints at this site. We knew we had no more than about 2 weeks to get off the ship, set up our drill equipment, drill cores, and then get everything back onto the ship before it needed to leave from the site. And we managed to do that. And so I want to take you through now mostly just some videos of what that looked like. So then we can talk about, the human experience of collecting ice cores and also what they can tell us. And I certainly will give Julia some space to share her thoughts on this crazy last year and a half or so that we've had out in the field. So let's see, I had this again, but I'll skip through it. So Julia and my work and Julia's PhD sort of centers around what we call ice rises in Antarctica, which are little pancakes of ice that ring the edge of the continent, which are particularly good for studying the complex interaction between the sort of atmospheric climate, the ice, these big glaciers that are starting to accelerate or melt more quickly, where they flow into the ocean. And so in our discipline, there's a lot of complexity in how these three parts of the Earth system interact. And we have very limited records in time and in space of how that interaction happens. So we've been trying to contribute ice core records to that, where we can get a couple 100-year record of how the atmosphere particularly has been pushing around glacier systems and the ocean systems down in Antarctica. And just to give you a sense of where we went and why, I'll put up here the huge Antarctic continent. You can fit all of the lower 48 states in here and still have room for Mexico. So these are all the permanent research stations that are occupied year-round in Antarctica of various sizes. And if we put on here that what we call these ice rises, these areas in red, these are places that are really ideal for ice cores. They're sort of just perfect little pancakes of ice with all the layers of information going back in time. And we've drilled quite a few of them over the years. But there's a bit of a gap both in where the research station dots are on here and where the blue dots are. And so that's this coastline, the Pacific coastline of West Antarctica. And so I've been trying, I guess, with the early part of my career to get us out there and to collect a new ice core. And now we did it just this last January and December, last January at this place called Canisteo Peninsula. So for the next just like maybe 5 to 10 minutes here, I'll take you through what that looked like, because it was, I think Julia probably would agree, one of the more intense experiences of our lives. And yeah, we're really proud of what we were able to accomplish with our South Korean colleagues. So our trip was, let's see, right around 50 days from New Zealand to New Zealand, but via these long legs over across the South Pacific Ocean to a region we call the Amundsen Sea, which we're really concerned about for how it interacts with some large outlet glaciers. And when I say large, Thwaites Glacier, the most concerning glacier in the world, is about the area of the state of Florida. So these are really big systems to understand, and we need a lot of observations to do that. But this is probably the most difficult region to get to on the planet for doing this sort of work. And then especially to have to bring back a couple thousand pounds of ice to analyze back in labs. It's a journey, to say the least. So I don't have a lot of great videos to illustrate what it's like to sail across the Southern Ocean on an icebreaker. I'm very lucky that I discovered I do not get seasick, but I'll illustrate what it was like by showing the books in the library on the ship. And this was, I don't know, not a particularly intense day, but it is a lot of back and forth. And it gets less choppy, but more interesting when you get near Antarctica, where you start moving through sea ice. So I think there's some sound on here. Works its way through sea ice leads, and it can push through relatively thick ice. It always tries to find the path of least resistance to get and then eventually we were able to get right up within a kilometer to within a kilometer of this pancake of ice that we managed to get out on and do both some ground-based surveys. The black lines there are lines that one of our colleagues drove with a snow machine and collected radar looking into the layers of snow and ice down to bedrock. And so we had an ambitious goal with a team of 8 to be out there for 2 weeks, if we could get that amount of time off the ship, to collect 2 different 150-meter deep ice cores with a drill that we brought from the US and then a drill that the Koreans had. And having those 2 records lets us both work independently as international partners, replicate our records, and also have some duplication. We actually stored the cores in separate freezers on the ship. In case one freezer broke down, we'd only lose 1 core and still have another backup. So the rest of this is just what it is like to do this sort of helicopter-supported work from a ship, which is quite rarely done. These sort of large camps working off of a ship with helicopters might happen maybe once every other year, and almost exclusively done by the South Koreans because of the capability of their ship and their helicopters. So you start by getting off the ship, and we try to be as close to the ice edge as possible to minimize our time over open water, which we don't want to end up in. And the ship is very much on its own. We're about a week sail from the nearest research station with medical capabilities. So you're very much out there on your own, and bringing in an entire camp with helicopters means something like 15, 20 loads of equipment dropped ice up, and then the same on the reverse. Here, maybe talking to the pilot, because it's quite challenging to fly over the white snow and for them to know exactly where the ground is. So there's a lot of back and forth there. But we got our camp set up, and we knew we were sort of racing against a storm that was coming in hit us. So we were very lucky to get off the ship before the weather turned bad, to set up our camp. And we had a very exciting first night. Wind starting in sort of 15 to 30 knot range, and then getting so bad that I don't even have video that I can show you. I think that's Julia's tent right there that she was sleeping in. Um, and so when you know a storm's coming, you sort of just hunker down and try to tighten things up so they don't blow away. But unfortunately, the next morning, our largest tents had been crushed, which is better than blowing away. So we were able to hang out in the tents, wait for the weather to get a little bit better, and then dig them out. And we were all pretty proud at the end. We kept using this tent, limping along for the next 2 weeks. And every time it got sort of crushed again by the snow, we'd just unbury it and do it again. After about 2 days of storm, I think it was, we were able to quickly get the drill set up. And so this is a little walkthrough of what our drill system looks like. So we power it with small generators. Um, and this drill is provided by a center called the U.S. Ice Drilling Program at the University of Wisconsin. And our drills are just a sort of a small winch that suspends a drill sonde that goes downhole, shaves around a cylinder of ice, and then pulls that cylinder of ice back up to the surface. So there's Julia in there again. So that's what the drill itself looks like. You bring it up, disassemble it, so that you can push out your ice core. And in this one, we're doing sort of 1 meter at a time. And then you get it back down the hole to get the next core as fast as possible. And it's just a race to do this process as fast as possible and keep the drill working, try not to make any mistakes. And we were working as long as we could. And otherwise, the only other thing we were doing was either eating or sleeping, because we knew we only had 2 weeks to do this. And so we were getting great ice cores. You can start to see some climate information here. This is the melt layer in the ice. So it is cold here, but on the coast of Antarctica, it does melt in the summer times a little bit, which is a melt layer is a really nice direct observation that it was near freezing or slightly above freezing at the site that day. And so records of the number of melt layers through time are a really direct record of temperature we get from ice cores. When it's not being super stormy, it is really, really beautiful in Antarctica, and the light conditions are always changing. These are some really cool halo formations and how the light moves through ice crystals that are suspended in the air.
Very cool.
And before you know it, it's time to be done. So we really, yeah, worked ourselves as hard as we possibly could, knowing that once we got back on the ship, we'd have nothing to do. So there's no reason to leave anything sort of out there on the field. And then we had to sort of do everything that's again in the reverse. So package up all of your ice into these boxes and then use the helicopters to get the boxes back into the freezers on the ship. And I wish I had footage of everybody on the ship helping us on the fire lines and everybody moving the ice core boxes as quickly as possible from the heli deck to the freezers. But the entire ship pitched in to do that. And we were able to, yeah, safely get these really, really hard-won samples into the freezer, and wrap things up. So this is what it looks like flying from our site, about a 10-minute flight from our site back to the research vessel. And sort of just like that, this really intense 2-week experience collecting this ice core. For me, especially that I've been trying to get us collecting these kinds of cores for about a decade. And it all happens really fast, and then it's over, and you sort of can try to process what you just accomplished. So that's most of what I have. I mean, really incredible experience. And if you want to read about it in another format, I did chat with a journalist sort of all through the expedition, and it was covered in Science Magazine earlier this year. And I probably need to send a thank you note to a colleague because the tagline that the editor chose for the article was this daring James Bond mission to drill Antarctic ice cores could reveal future of sea level rise. So probably the most generous description of our work that we'll ever get, but it was pretty wild culmination of a year and a half or so with multiple field projects that sort of led to this this huge accomplishment that I'm very grateful Julia help pull off. Our drilling team was me, Julia, and our driller from Canada. So very small teams working in really intense environments, but happily made it through. And this was our proud team. So the Korean team and our US team and our pride and joy, our destroyed home behind us that kept us safe for 2 weeks. So yes, that's probably more slides than you usually get at a little chat like this. So I'll stop there and we can just take questions. And it'd be great to see any faces on here if you'd like to turn your cameras on, but no pressure.
Thank you, Peter. That was fantastic. I have a ton of questions, but I would love for our audience to have a chance here. So we will open it up. No need to raise your hand, just unmute, or feel free to toss some questions in the chat.
I have I have what's perhaps a silly question, but when you get those really long cores out, at what point do you like flip them without like having a problem with the top of the tent and like the back? And I'm curious about those logistics.
Yeah, we usually drill the cores in like 1 or 2 meter increments. And so when they're 2 meters long, they're a little bit more delicate and you have to be careful. But yeah, Julia was what we call the ice core handler in both of our recent field expeditions, which means it's your job to measure the length of the core, bag it up, and most importantly, put an arrow on it with the arrow pointing towards up, um, so that nothing gets flipped out of sequence. Yeah, critical stuff.
What is the timeline for the subsequent analysis? Is this the type of thing where this one core will become 10 dissertations over a decade, or you know,
Yeah.
how you talked about it taking a decade to get the core essentially, but
Yeah, ice core science is not incredibly fast, and especially in these cases when we're proposing to collect new ice core records in places where we're not sure that we're even going to be able to get them. And that applied in both of these situations in the last year, that the site at Mount Waddington in British Columbia. A challenge is that we get funding just to collect the cores. And so now, I still need to go back to the National Science Foundation and ask for now funding to take the cores through sampling, so cutting them up with bandsaws or portions of them up with bandsaws to get samples for chemical analysis. But yeah, certainly they do then, once you have them safe, especially in our National Archive in Denver, you can go back to them again and again. And yeah, I don't know about 10 dissertations, but certainly several dissertations, to squeeze all the different information out of the cores. So yeah, I feel like I'm behind on accelerating us into the next step of analysis and interpretation, and then of course publication. But I'm also trying to give myself a little bit of grace in that we expended a lot of myself in the last year and a half to just get these cores and have the expeditions all work out. But yeah, it'll hopefully it'll keep us busy now for sort of similar timescales, 5 to 10 years. You can really learn a lot from these cores.
Well, I have a quick question. You mentioned, Peter, that you were, so far away from other research stations where there's, medical staff and supplies. What is the protocol if there were some sort of medical emergency? Is there someone like on your team that has some expertise, or what would happen?
Julia, do you want to answer that? Just like what's on the ship? And we certainly had to think about those things once or twice.
Yeah, it's a great question and something that we thought about, and I was certainly a little nervous about because this is a environment that I was extremely unfamiliar with. But prior to even boarding the ship, we were required to do a boat safety course that we took down in Texas, and that was, safety things on the ship that we should be aware of, as well as how to put on a Gumby suit, just the fun bright orange, large, way oversized suit for flotation. And then when we were on the ship, when we first got there, we, learned emergency exits, more so emergency vessels to get to in case of any sort of emergency. And then when it came to us being on the ice, we were far, and the ship actually did proceed to do other science in other parts of the coast than where we were. But we had a safety guide with us. His name was Lion. He was wonderful. He was a mountaineer, and he was there to sort of ensure that we had water at all times, and ensure that our tent situation was safe. And he accompanied our radar expert, who was on a skidoo, like a little jet ski, snow ski situation, and was traversing across. So he went with him to ensure that was safe. And I think in case of like major emergencies, we did have constant communication with the ship to ensure that they knew we were okay. We had daily check-ins with them. And then we also had sat phones, so all of us were connected. And then we also had Starlink set up when possible. So we had access to Wi-Fi in case of anything. So I feel like in the end, we felt fairly safe. And thankfully there was no major emergencies, but in case of anything, we did have constant communication with folks.
Yeah. Yeah, and there's a doctor on the ship when it's this far out as well. So a doctor and a nurse. We did have one unpredictable factor when you're doing this sort of expedition way out there is that there are fishing vessels all around the coast of Antarctica, and law of the sea dictates that you have to respond to any medical emergency if you have those resources. And so we did have a Uruguayan fishing vessel that thankfully right near the end of our science window, we had to go over and send a small boat over with the doctor and actually a graduate student from the US who spoke Spanish. He was from Colombia. Because unfortunately they had a crew member who had had a stroke, and he was stable. They gave him some medication, but then advised them to go back to port as quickly as possible, which is 7 days sail, which can be really impactful for them. If they have fishing quotas they're trying to meet, of course, there are pressures for them to not end their expedition. So anyway, thankfully we were concerned about needing to take that person on board potentially, and then also take them 5 to 7 days to the US research station, which does have good medical capabilities. But yeah, all to say, you're way out there, and everybody, I guess the upside is that everybody who's there with the National Antarctic Program that has resources is ready for any needed emergency response. So it's got pretty good international coordination.
I think the James Bond headline was accurate. You guys are pretty intense, but that's amazing that you're able to help those folks out and there are no major emergencies with your team. Any other questions for Peter? I know we want to give Julia some time to share her work as well.
I have a question about when you're doing the chemical analysis of the ice cores, like what does that look like? Right? Like what are you taking a chunk of core?
Yeah. I can illustrate that, I guess, with a quick video here. So one of the things we do when we sample things is let's see, we cut up samples. We often just cut a stick of ice, and then so like this is cutting up the ice with a bandsaw. It's a little bit different, that one. But then one of the ways we analyze cores is called continuous flow analysis. So this is a close-up here of a stick of ice about 3 centimeters wide that we put on a heating element to melt the ice and then plumb that water away either into sample canisters or directly into instruments that can measure all the different things we're interested in. So we, I guess in our community would say we either sample things discretely, which is cutting up, as small as like 2 centimeter thick samples, or we have continuous analysis, which is that like putting a stick on these melters, and that tends to be the highest resolution that we can do. And anywhere, yeah, you're sort of getting at two centimeters of vertical resolution in our sampling, which depending on how much snow falls at the site per year can impact the resolution of your record in time. So there are places in Antarctica, say, where we get the 800,000 year long record that it only snows 2 to 5 centimeters per year. And so your sampling resolution ends up quite low. Where we were on the coast of Western Antarctica is some of the snowiest parts of Antarctica. And then our layering there is probably on the order of 1 to 1.5 meters per year rather than the centimeters. So we're going to have really high resolution cores, probably only 200 meters long, because if it snows that much, you can't squeeze as many years into that 150-meter depth that we were able to reach. Yeah, so you have to balance all those things based on where you're going and what your research questions are, what you think the ice is going to be preserving, that sort of thing. So there are a surprisingly large number of questions you can ask with ice core samples, just because they preserve the chemical impurities in the snow and also those gases in the ice. They preserve them so well that one of the projects that I work on is reconstructing not only carbon monoxide concentrations in the ice, but radiocarbon levels in that carbon monoxide, because it's just absolutely perfectly preserved. So yeah, ice cores are endlessly fascinating and really provide us a lot of concrete information. And I don't know, I don't know if I briefed Julia to really prepare a spiel about your research, so don't need to put you on the spot, but certainly, that or any reflections on the field work.
Yeah, I'm happy to provide a little insight. So essentially, my PhD has been very privileged to be able to go with Peter on all of these expeditions. I think, it's rare that we get the chance to go somewhere so special like Waddington or Antarctica. And it just so happens that my actual thesis is not really dependent on either of these field expeditions. So it was just a great opportunity to be a part of them and to now care a lot about those ice cores and all the efforts that we put into them. But a lot of my work does involve those ice rise sites that Peter talked about in depth, and I can share just like a couple of old posters that I've made, just to give you a sense of, how do I see?
I mean, just for context, Julia started her PhD in fall 2020.
It's
And
true, yeah.
this project on the icebreaker was not even, I did not have an inkling that it was even possible at that time. So a lot has happened over the last 4 years for all of
Yeah.
us.
Yeah, and I would say starting during the pandemic when, I moved to a new state that I've never even visited before, when the university was shut down, it was an adjustment to be like, okay, I'm actually a grad student. I'm not just in this COVID bubble. But being able to do fieldwork has really allowed me to then just connect with our greater community as well. One thing I will say about being on the ship is that it was this very international group, which I think is just a wonderful opportunity to get to know, what the South Korean groups are doing. But then there was also a Swedish group, and then there were folks from BAS in the UK. So it was just really wonderful. We had the 2 intense weeks of extracting our ice core, but then we really had 2 months of being able to talk to folks and collaborate and just learn about what their science was. But this is a lot, and I won't go into too much detail, but essentially, besides ice cores, there's a lot of information that we can extract from these ice rises before getting an ice core. And this information can range from using modeled climate data. So ERA 5 and MERA 2 are what we call reanalysis data sets, and they essentially take observations to create model data of what we think the temperature, precipitation, wind, et cetera, conditions were from 1979 to now. It's sort of more of a trusted data set that we have. So that's sort of what we have over here. We're in Martin climatology. And Martin is the focus of this poster because at the time we thought Martin was our goal ice rise. We ended up going to Canastillo, but Martin is still an important ice rise for us. And then another thing that we sort of I've been working on besides using these reanalysis data sets is also looking at precipitation pathways. So there's a model instrument called HiSplit where you can actually put in where you want to look, and then it'll track the precipitation pathways, so back trajectory models of where your atmosphere particles are coming from. So we can look at certain locations and sort of get a good sense of if we have precipitation, where is it sort of sourced from, and how does that change the dynamic of the ice, ocean, and atmosphere dynamics that we're seeing where we want to take an ice core. So essentially, a lot of my work is just background data for taking ice cores, and it's essentially giving more data and evidence for why we need more ice cores because model data can only take you so far, and observation data is what we really need, and you get that through ice cores. So this is just a lot of words and graphs and stuff, but that's sort of what I've been doing, and it's just been an additional pleasure to be able to go in person to these places because it helps bring a lot of context to the work that I'm doing. So, knowing that West Antarctica is a super dynamic place with high winds and a lot of accumulation, that's one thing to know that. And then it's another thing to then be there and experience it and feel it and see it and, truly get a sense of, okay, this is a very intense place and I now know it from firsthand. So yeah, but happy to answer any questions about the experience as a grad student from a grad student perspective, or share anything else folks are interested in.
Yeah, I mean, we sort of set up Julia's PhD so that it didn't require any of these, crazy end of the world expeditions. And it's, a lot of that background and sort of using the existing data sets, which are very imperfect, to sort of demonstrate the value of like, hey, if we could go to these places and collect real samples, we probably would be able to learn about these things. And it's a lot of that background work. She's helped me being the pitch person, sort of selling these the need for this work. But yeah, and then you end up there and, within 10 hours of arriving on Antarctica for the first time, I think you got trapped in your tent by the snow for overnight or something like that, which I still feel bad about.
Yeah, a good 24 hours being trapped. But yeah, it's part of the job.
Thanks so much for sharing that, Julia. It's fascinating work. Any questions for Peter or Julia?
I'm just curious what got you both interested in this kind of work? What led you to where you are today?
Yeah, that's a great question. I mean, I got into this work very luckily as an undergraduate at the University of Washington, which was my state school growing up. But I think that what really fascinates me and my discovery of ice cores sort of coincided with my discovery of geology and earth science. And I think I've always had an interest in history, and the geologic record, allows us to explore that over the entire 4.2 billion year history of the Earth. But ice is like the youngest and most actively recording natural archive on the planet. And so that's just endlessly fascinating to me, especially once you sort of learn the basics of climate change, that like we are so incredibly lucky to have glaciers recording information about atmospheric greenhouse gases going back in time, because otherwise we would be very much guessing about how our current rate of change in our greenhouse emissions is put in context in the past. So yeah, just totally fascinating. And it's just beautiful to look at. Like ice, I don't know, there's so many aspects of it that speak to me. But Julia.
Yeah, I mean, I think I've always been interested in the environment. I didn't necessarily grow up camping. grew up hiking and enjoyed the outdoors, but I was a city kid. So, in undergrad is when I started to get sort of into climate research and did a couple of expeditions, field work trips to Great Basin in Nevada, which is a very cool, very underrated national park. And we took sediment cores. So that was my first experience with coring. And that's essentially just, soil cores from the bottom of a lake. And we created this record of fire history with charcoal samples that we were able to find along the core. And that to me was my first, like, holy cow, this is amazing. We can find out what happened in the past just by what already exists in nature. And so that was interesting and fascinating to me. But then I realized that you could also do that through ice. And sediment cores are cool, but ice cores are way cooler. And so that was a motivation. And then also, I did a master's degree in England that I looked at a bunch of ice shelves around Antarctica and used satellite imagery to sort of track their changes over time. And that just got me obsessed with this continent, because you're constantly staring at images and seeing how they're changing over time. And you're just like, this is incredible that it's happening all the time. And we just don't know as much as we possibly can about it. So I think that was also a motivator. And then connecting with Peter back in 2019, he had these great ideas and had this Waddington project on the horizon. So I just was like, yeah, take me with you wherever you go. So that's where we ended up.
Yeah, it's worked out. That's a question there from Austin about the future of our research and the future of this type of research in general, which are two, very good questions. I'm still wondering whether or not we might actually be able to join the Koreans on their icebreaker again. Not this December, but next December. They're scheduled to go back to the same region, and we could get more cores from a couple 100 kilometers away. Start sort of filling in gaps we have along that whole coastline of West Antarctica. So I hope that's possible. I hope we also can potentially do this sort of work with the U.S. Antarctic program at some time in the future, but don't want to get into it too much. But the U.S. Antarctic program is actually in a really, really tough spot right now that due to stagnant funding over many, the last decade and a half, and now budget cuts. And unfortunate timing of starting some infrastructure rebuilds and then being hit by COVID. So we actually, this year is the first year in my career and in the careers of any of my colleagues, I believe that we're not allowed to even propose new field science in Antarctica through the National Science Foundation right now. We've always had an annual solicitation where we can at least send them our ideas and they can select the best ones to support within their capabilities, but they actually, well, in addition to cutting science projects in half down there in the last year or two, they are now not accepting new ones, which is challenging, but also good that the program's admitting that they can't support what they have in the past, and so they're trying to actively rebuild. But on timescales for myself as well, but especially for grad students like Julia, the National Science Foundation is telling us that they hope to be back sort of in full capability by the early 2030s, which has been really, really challenging. And our program officers are directly telling us, like me as a pre-tenure faculty member, to not base your tenure on Antarctic fieldwork related projects. And I think I've managed to sneak around that by finding this international collaboration. But it's a really tough time right now, and I think the broader university level, keeping an eye on federal funding for basic scientific research needs to be more of a priority for us than I think it has been. And I think a lot of the challenges we're in polar programs within the National Science Foundation right now is due to a little bit of resting on our laurels over the last 10 to 15 years and enjoying a really capable program, but not looking down the road. Of course, nobody could see COVID coming, but I think if you see stagnant funding levels since the late 2000s, you shouldn't assume with rising costs that's going to have an impact. And so that's definitely something that's on the radar for us. There are, I certainly have more goals for research in Antarctica, and I'm ready whenever we can start sending our wacky ideas out there again. But for right now, we're sort of in a holding pattern in the Antarctic setting. But one thing that I do hope we can do in Antarctica, a lot of the ice cores that we will compare our new records to. So we now have a record that'll go from the year 2023 back 200 years. The nearest ice core records that we can compare to were all drilled in like 1999 or 2000. So we also actually need to go back to all of our old ice core sites, because most of them in Antarctica were drilled in the early 2000s or 2010s. So that's a good amount of work to do at some point when we can get back out there.
Any final questions for our speakers?
Yeah, I've got one last question actually, if that's possible.
Hmm.
Yeah, I know, Peter, you at one point were working on kind of an undersea internet cable to Antarctica. But I've also seen stuff recently that with the Starlink satellites going up there, that's kind of changed things a little bit. So I guess, yeah, I don't know. I was just wondering if you had any thoughts on like the status of that, or if that's even going to be a thing anymore, possibly now.
Yeah, that's a great, great question. And we hosted a workshop here during the pandemic. I mean, here we hosted a virtual workshop at the request of the National Science Foundation to sort of scope the science impact like building a subsea fiber optic cable between New Zealand and the U.S. Antarctic Research Station McMurdo, which is by far the largest in Antarctica. It's about 1,000 people in the summertime. And it's an interesting potential project. And certainly right now, so the National Science Foundation got an 8% budget cut back in the spring. So it doesn't seem like a great time for that. But big technology infrastructure is sort of high priority for the National Science Foundation. And so I think that the idea plays to that and what the director of the National Science Foundation is thinking for it. It is, Starlink has emerged as a very capable commercial service just in the last 2 years. So I think it does change some of the considerations on needing a fiber optic cable to actually get better internet in Antarctica to, send data back and forth and do more remote working. But those low Earth orbit satellites aren't as high bandwidth as a fiber cable. And I think from a scientific standpoint, that a fiber optic cable is an observing platform itself. So if you have a cable that's draped across the Southern Ocean from New Zealand to Antarctica, that's actually a really key segment of the Southern Ocean where a lot of really big ocean water bodies form. Deep water bodies that then spread across the entire Pacific Ocean. So there's a lot of new tech around using fiber as a sensor for pressure sensing, temperature sensing, acoustic sensing. So a fiber cable would be a piece, a physical, like a scientific observation platform, basically. And so I think that gives it some legs still. So sometime late last year, there was an engineering study that was released that NSF paid for that sort of scoped the feasibility that, like, yes, you can infrastructurally, it would work. It would not be super vulnerable to icebergs or landslides or things like that. It probably also had a price tag, which was redacted in the public version. But the price tag for something like that is going to be in the sort of $200 to $400 million range. So it's the annual budget for all of NSF's polar programs is about $400 million. So it'd be a big extra initiative the National Science Foundation would have to go for, but certainly it would be a first for Antarctica and would sort of continue along the lines of US leadership in Antarctica, which the way that Antarctic science works, it's sort of all about trying to compete around science and avoid competing in other bad ways in Antarctica. So we have a really strong treaty system down there. Yeah, so I don't really have a good sense going forward. It's just not really an optimistic feeling time right now for the NSF, particularly in Antarctica, and with federal funding and a lot of uncertainty around the future of federal funding. In this year, election years are always a little bit stressful for that. So, yeah, a lot of uncertainty, but we still have a lot of critical questions in Antarctica that we know we need to be pursuing. And so we will be, back to having the world-leading national Antarctic program by the 2030s. I'm confident, and we all on the science side will continue to support the National Science Foundation how we can, and always be pestering them to do better and do more. And yeah.
Awesome. Yeah, thank you.
Thanks, Peter. With our last moment or two, I would like to put Julia on the spot, who creates some really cool art around her work with glaciers. And I think that art is a fantastic way to communicate about climate and to reach different audiences. So I think it's amazing that you're interested in both science and creating art about the science. I think it's wonderful. So if I can put you on the spot for just a moment.
Yeah, no, I appreciate it. I that's a huge thing that I think I've been thinking about a lot, and especially during the pandemic was, you know, if we're isolated, if we have a small lab, like how can we make it an accessible science for folks to get interested in and learn more about without it being intimidating. So over the pandemic, I sort of got into this what I call paper collage art, and these are just a few that I have on my website because every grad student feels the need, I guess, to have a website. But yeah, so some of them, like this one and this one, are representations of Mount Combatant, and they were based off a picture I took while we were up in Canada. But essentially, it's a collage, digital collage, so taking pictures of paper, crumpled paper, and then layering it, and then sort of coloring it digitally, and trying to create these images. I found that crumpled paper sort of did a really cool job of representing ice, and representing sort of the multi-structural, like 3D aspect of ice. I mean, it's white and it can be sort of plain, but then you look closer and it's got all these different cracks and formations within it. So something that I've played around with. But then I think my interest in art has also led to them being the sticker person for the community. So that I think is also a great way of sort of showing what we're doing through stickers, because who doesn't love a sticker? So Ice Crew is a early career focused workshop that we have every year in relation to the Ice Core workshop. But it's where we invite early career researchers within not just the Ice Core community, but whatever sort of ice community we have, to talk about things like, what's the job aspect look like after a PhD? If you want to stay within academia or outside, how do you write a proposal, and how do you, write papers? So we're just exploring that kind of thing and trying to make it more educational. So thankful to be the sticker person for that. And then this was our sticker for the Combatant Coal Ice Core, for Mount Waddington, and then this is our Rika sticker for our ship and helicopter expedition. And this was another Ice Crew sticker. But I feel like it's been a fun time to sort of take breaks away from the academic side of things and be a little more creative. I think it's really important to utilize both sides of the brain in that way. And if that creativity can reach people and make them interested, then that would be wonderful. Demi, who's also actually on this call, and Peter's other student, and I have been noodling with the idea of creating a children's book with art. So that is something, when she's here this weekend, that we will talk about. But yeah, just ways to educate, I think, is always important.
Julia.
Well, I've been grateful to have a
Fantastic.
sticker person. Stickers are like currency in Antarctica. It's how you say thank you to people who are helping your project.
Is wonderful. I love the interdisciplinary aspect of this work. Julia, that's fantastic. Really quick before everyone hops off to the rest of their day, this coffee chat series will continue next Tuesday with a chat on solar, and then one in October and one in November, looking at agriculture and food security, again, all from this climate lens. So I would love to see some familiar faces at these upcoming chats. And just a quick round of applause for our speakers, Peter and Julia. Your work is fantastic. Thank you.
Yeah, thanks for having us.
Thank
Yes,
you.
of course. Awesome. Well, everyone have a fantastic Friday, and I hope to see you all at a future chat.